So far, when we've talked about stress, we've ignored one detail. It's a pretty important detail in geomechanics, and that is that the rock, the material that we're interested in studying is actually filled with fluid, okay? And that fluid imparts an additional load. We talked about like vertical stress. There's simply the weight of the earth on top of the reservoir that we're interested in can cause an external force. Well, the fluid pressure that's in that reservoir can cause sort of an internal force. And so if we were to look at this little pore network that I've drawn here that's embedded in our representative little cube of material, then we have the external stresses due to tectonic motion and the weight of the earth. Then we also have an internal force on the rock. So any little characteristic piece of material in here is going to feel the internal force due to the pore pressure and the external forces, okay? And that's going to affect the strength of the rock, right? So really soon we'll learn some constitutive and failure models to determine when rocks are going to fail, and the pore pressure can play a role in this, okay? In fact, what do you think happens when the pore pressure exceeds the minimum principal stress? Yeah, so if the pore pressure exceeds, these are compressive, right? These are compressive. So if I increase the pore pressure and to the extent that I exceed the principal stress, which are all compressive, I therefore put the rock into what? Tension, right? Are rocks very strong in tension? Typically? Not really, right? So typically if you put the rock into tension, you're going to fail it. And due to the nature that the pore network is typically filled with a fluid like water, there's a name for this, right? Well, so we're talking about water and fracture. There's a name for it. Hydraulic fracturing, right? Yes. So anytime the pore pressure would exceed the external pressure of the principal stresses, and you put the rock into tension, then you're going to hydraulically fracture it. Of course, we do this by design as a stimulation technique, but it also occurs naturally in the earth too. Right? Most of the faults and small natural fractures in the earth are, well, many of them were there as a result of hydraulic fractures. So, when we talk about pressure, like, does anybody remember from thermodynamics how you define pressure? It's like the rate of, thermodynamically, what is pressure? It's like the rate of change of internal energy with respect to a change in volume, something like that. Partial E, partial V, or maybe the negative of partial E, partial V. So that's pressure. That's clearly internal energy is a scalar, volume is a scalar. So pressure is clearly a scalar, right? When we talk about pressure, it's a scalar. It's not a tensor. It's a scalar thing, right? And so when we include its effect on the total stress tensor, which we know as a tensor, the pressure acts in an isotropic way, okay? And so basically what we do is we define this notion of an effective stress, okay, which is the total stress tensor minus, so this is the total stress tensor, that's a tensor minus the pressure, the pore pressure, times the identity matrix. So the effective stress is the total stress minus the pore pressure times the identity matrix. So it operates on the stress tensor in an isotropic way, okay, only along you know, if you remember, we talked about the normal stresses are sort of the hydrostatic stresses are the ones along the diagonal of the matrix. So of course, if we then transform our total stress tensor into principal stresses, where then we only have diagonal entries, then it's, you know, just the principal stresses minus the pore pressure. That gives us our effective stress. So if we just combine the terms, then you get this. And one thing we'll learn really soon is that faulting, or whether a frictional interface in a rock, a joint, a fault is going to slip or not depends on the effective stress. Essentially, if the pore pressure is increased such that it exceeds the frictional interface conditions, then the fault will slide. Okay, so that's one application of why this is important, and we'll see it really soon when we do fault resolution, stress resolution on faults.